Hey guys, it's Luke and welcome to some physical chemistry. This is, unfortunately, quantum chemistry, probably one of the least favourite parts of chemistry for a lot of people, including me. Well, I prefer it to organic chemistry, but anyway, we're going to be talking about quantum chemistry, and first off, the postulates and assumptions that we have to take into account when looking at wave functions, or just quantum in general. So, the first postulate is that a system is described by a wave function, and the wave function contains all the information about the system. There are constraints on the wave function, such as the acceptable wave functions should be single-valued, continuous, not infinite, and have a continuous slope. So some examples of the unacceptable wave function are shown below. This one here is unacceptable because it's not continuous. This one here is not allowed because the derivative is not continuously positive or continuously negative. As you can see, it goes down and then goes up, so it's got a positive and a negative gradient. This one is not acceptable here because it doesn't have a single value. As you can see, there's multiple values here, 3 at that point. And this one isn't allowed because the wave function goes to infinity, which means there's no finite values, and the wave function has to be finite in order for it to be an acceptable wave function. So we've got some observables here which are represented by the operators. For example, the momentum operator. So we've got the momentum operator here is equal to minus I h bar, which is reduced Planck's constant, and then that's the first differential with respect to x, I being an imaginary number. The values of the physical measurements correspond to eigenvalues of the operator. So there's just a simple eigen equation almost, where you've got the operator and a wave function, where you've got an operator acting on a wave function is equal to the eigenvalue acting on a wave function. So we've got some eigen equations. A common one is the Schrodinger equation, where you've got the Hamiltonian energy operator acting on a wave function, and then you've got the total energy acting on a wave function as well. The eigenvalue must be constant, which is a key thing here, and the wave function eigenvalue must be independent of x. So we've got the operators, which for example is the Hamiltonian. These are representations of mathematical operations. For example, using that omega there, is we can say the omega corresponds to differentiating twice. There you go, with respect to x. Then we've got the Hamiltonian. Hamiltonian is a Hermitian operator, meaning it has the following properties. The eigenvalues of a Hermitian operator are real. For example, not a complex number, which is I being the complex number. So if we have just a simple equation, z equals x plus iy, the complex part is the iy part, and that's because I is the complex number. But we know that I squared can equal minus 1, so if we do the complex conjugate of z, which is z star, we can get we can get z star equals x minus iy, because that's doing the inverse essentially of z to make it almost a real number, you know? Because if we square I, we get minus 1, which will be the same as if we did it for z, I suppose. I think that's what it's saying. Anyway, if you combine z star and z as a multiplication, you'll get a real number, because you get these two things here, which is a z component there and a z star component there. You'll get x squared minus I squared y squared, which will be, obviously, we know that I squared is minus 1, so that term will cancel out, so essentially you're getting x squared plus y squared. So, I'll move this up a little bit. We've got eigenfunctions, and these need to be orthogonal in Hermitian operators. So, we can look at wave functions, and both of these factors can be taken into account when looking at wave functions. They can either be normalized or orthogonal. When a wave function is normalized, the multiplication of the complex conjugate of the wave function, and the wave function, when integrating over all space, has to equal 1. And for when two wave functions are orthogonal, the multiplication, or the integral of the complex conjugate of I, which is different to the wave function of j, when integrating over all space, d tau, is equal to 0. And you can also write that as essentially this. So, to put in short, well, I'm going to call that delta ij because that's what it is. So to put in short, delta ij equals 1 when I equals j, and that's when it's normalized. And delta ij equals 0 when I doesn't equal j, which means that's orthogonal. So, as I mentioned earlier, I and j are different eigenfunctions, which, for example, could be the ground state and the excited state. Next up, we're going to talk about the expectation values. So an expectation value is represented in a bracket notation, which corresponds to being the following below. So this essentially is equal to that. That's what it means. So the expectation of this omega is the eigenvalue. So we've got this here. We can replace out. So let's say the omega is telling us to do a function of omega on something else. We can take that out of the integral, so we make it eigenvalue independent. Say that this is equal to 0, and then we'll get a w, or equal to 1, sorry, when it's normalized. And then we'll get the omega on its own. So there we go. Finally, we've got the Born interpretation, and we've got a bit of bracket notation, and then that's all we'll finish, I think, today. Let me just check what we've got later. Oh no, we might as well continue. So we've got the Born interpretation. So if the wave function of a particle has the value of over wave function at a point r, then the probability of finding the particle is proportionate to the wave function squared when integrating over all space d tau. So I've wrote that twice there, I don't know why, but that's just what it means. It's essentially the wave function's complex conjugate times the wave function is the wave function squared. And the probability is equal to 1 due to normalization. D tau will be a small volume, which is infinitesimal. And d tau, as I said, is integrating over all space, which is dx times dy times dz. For example, it's a particle in a box, which we'll look at later. Then we've got the Dirac bracket notation. The bracket implies that we're integrating over all space. So, for example, we've got this here, which is equal to that. Simple stuff, really. And then we've got that is equal to that, which is very similar to what we had up here. Well, it's pretty much the same as what we've got up here. So the final few things, we've got the Heisenberg uncertainty principle to look at, and then I think we've got the Born-Oppenheimer approximation as well. So the Heisenberg uncertainty principle says that it is not possible to specify simultaneously with arbitrary precision both momentum and position of a particle, meaning we can't know the position of the particle and know its acceleration or momentum, but we can know one or the other independently, essentially. And here's the equation for it. We've got the uncertainty in momentum in the x-coordinate, and uncertainty in position of the x-coordinate is greater than or equal to half of the Planck's reduced constant. And this applies to all complementary or incompatible observables, which means you can't know both values to arbitrary accuracy at the same time, as I just mentioned earlier. We've got an example of this. So we've got a couple of operators there, and we're saying that's not equal to the inverse of the other operator. So we're saying that omega 1 times omega 2 times the wave function isn't equal to the inverse of omega 2 times omega 1 times the wave function. And this can be expressed as a commutator of the two operators. So if we write that, just ignore that. So if we've got that, we can say that that is equal to that once you multiply out the bracket. And then we can say if the multiplication of these times the wave function is equal to 0, that something's compatible. And if the multiplication of these doesn't equal 0, something is incompatible, which means they're complementary values. So there'll be some examples later where we will look at this, and that'll explain things a little bit better. This is just the basic principles of quantum chemistry. I'm not explaining them too well, this is just the notes that I've got, but the examples will help later on. So if we look at the Schrodinger equation, we've got a time-dependent form, which includes all of this mess, and this describes a system evolving with time. But for our module specifically, we're looking at the time-independent form, which is more important as it says here for this course. We've got the Hamiltonian times the wave function with which is dependent on the coordinates r, and then we've got the total energy. So essentially it's the Hamiltonian. And it says here this describes a system only dependent on the coordinates, which means it's stationary. The Hamiltonian is comprised of the kinetic energy and potential energy contributions. So we've got the Hamiltonian operator is equal to the kinetic energy and potential energy contributions. And in one dimension, the time-independent Schrodinger equation is what you can see there. As I said, it's not too helpful just going through the theory. The example should be helpful later on.